to learn exactly on how computers have been utilized in medicinal chemistry. You know, medicinal chemistry keep talking about issues to do with drug design, drug discovery, drug development, and so on and so forth. So with the use of computers and coming in of different softwares that have been developed by many different people, you find that computers and softwares have really been so helpful in medicinal chemistry when it comes to drug, most especially when it comes to drug design, and also to do with issues of optimization and so on and so forth. So with having said that, there are, when talking of these different softwares, like I mentioned, computers have come with different softwares which have been designed to help these chemists in designing different lead compounds and also issues to do with drug development, like lead optimization. So one of the softwares that is used mostly is the software that is used for the drawing of these chemical structures. I think I must have mentioned it, I must have talked about it in one of the previous lectures that we've been having about the use of ChemDraw. All right. So with ChemDraw, it's a very very friendly software which is used to draw these different compounds. So once you use, let's say, ChemDraw, it gives you information about, like, once you draw your software, your structure, okay, it will give you the name of the chemical name of the compound. You know, sometimes you may fail to give the correct UPAC name of certain compounds. You know, there's 1,4 di something, dimethyl, something like that. So sometimes you may miss it on how to actually give it the correct name. So with the use of these softwares like ChemDraw, once you draw the structure, you can put settings where it gives you the correct name of the compound. It will give you the molecular formula, the molecular weight, the mass, and also the other important thing it will do will be to give you the NMR chemical shifts. And why is this important? This is because with when you're actually working in the laboratory and trying to synthesize these different compounds, it's you deal with issues like on a daily basis when you're looking at any like chemical, you're trying to combine these different chemicals to make a compound, you need to know the molecular weight of the compound that you're going to make. Why is that important? It's because as you are trying to use different ratios of these different reagents, the ratios will be dependent also with on the molecular weight of that compound that you're going to synthesize, or the compound that you have synthesized. All right, and also besides that, it's also important to know the NMR chemical shifts, the prediction of the NMR chemical shifts. That is the proton NMR and the carbon NMR. And why is that also important? It's important because even as you are synthesizing these chemicals in the laboratory, you need to verify that what you have synthesized is actually the compound that you wanted to synthesize. And how do you verify that? You verify that by carrying out a test, that's NMR test, either the proton NMR, which is H NMR, or the carbon 13 NMR. So, but again, so once you do, let's say you make a compound, you synthesize a compound in the laboratory, then you go to the NMR to test. So once you test, once you test that, the NMR will give you the result of, it's unfortunate that I forgot to include it in the slides, but it will give you like information on a piece of paper on how the information about this compound that you have made. All right. So once you've gotten that information from the NMR, now you have to compare it to the predicted NMR results, which were obtained from a ChemDraw. So you now compare the two of them to see if what you have made, the NMR of what you have, the compound that you have made, is exactly as the one which was predicted, and that's how you confirm the compound that you have made. So you see that with the coming up of these softwares, they've made life very easy for chemists and medicinal chemists in general. And this is just an example of how the results that you get from a ChemDraw. All right. So you draw after you've drawn this structure here on your ChemDraw. These are some of the information that would come out. The first thing would be it would help you give the naming of your compound. All right. So the naming of the I'm told I'm not so audible. All right, I'm in the office and I may be noisy to the others, but anyway, I'll try to speak louder. Okay, so this is the structure. So let's start with your ChemDraw. This is the structure that if you've drawn this structure on your ChemDraw, and this is the name that you can obtain. After you've drawn the structure, maybe you're not sure of the naming of your compound. So with the use of ChemDraw, you can actually, it can give you the exact name of your compound. And besides that, I've talked of the other properties like the molecular weight, the mass. It would give you such information. It would talk about issues of melting point, boiling point, and so on and so forth. So this is a very good software. And also, besides that, there's also the predicted NMR results that I mentioned. I talked of carbon NMR and proton NMR. So with this NMR, at this position, there's a carbon atom there, carbon, and wherever there are these numbers, they are carbon atoms. So this predicted NMR is showing you that when you get the results from your NMR machine, this carbon atom here, it should show at position 3.5. The other one should be at 61.4, and so on and so forth. This is how you have to now compare. Once you have your results, compare and see if you're going to see carbon atoms showing on your the results that you're going to make in your you're going to have from your NMR, and if those carbon atoms are going to be at these positions. And also for your proton NMR deals with the position of the hydrogen atoms. So when you have the results, you have to compare and see if the carbon atoms are going to be seen at that position, of what you're going to have. So this is the issue with ChemDraw. So if you have any question, just take notes, then you ask me a bit later. All right, so that's with drawing of chemical structures. So we have identified that these computers are very useful in medicinal chemistry. And the first part is that they are useful in okay, somebody has a question, sorry. All right, so with questions with combinatorial synthesis, kindly let's discuss them a bit later. Let me deal with the topic at hand. Okay, so with we've talked about the use of computers in medicinal chemistry. We've mentioned that they are useful when you are talking of drawing of these chemical structures. And the other use is what we call molecular modeling. So with this one, molecular modeling, what we mean is that we are talking about the use of these softwares that help in the generation, the manipulation, the representation, and representation of three-dimensional structures of molecules. All right, so it looks at molecular modeling. So like with ChemDraw, it's helping you out in coming up with a 2D structure. But with molecular modeling software, its application, it's helping you to generate this three-dimensional structure. And associating that structure to the physicochemical properties. Some of the physicochemical properties, we did talk about them in the other topics which we talked about. So that's what ChemDraw will help out with. It will help you come up with a three-dimensional structure with the use of the computer. All right. So so when you're using this software or this application to come up with a 3D structure, you are trying to manipulate or you are trying to construct these molecules by taking note of the atoms that are found in this compound that you are making, that you are designing, and also talking of issues to do with bonds. All right. So an example would be, let me take you back to this slide. So if you're drawing this compound, you have issues to do with atoms. We've got carbon atoms in here. We have nitrogen atoms. We have oxygen. We have got hydrogen. So you're taking note of these different atoms and also the bonds. All right. So you've got carbon bonded to another carbon. You've got carbon bonded to hydrogen atoms.
It's 9 hours.
Carbon bonded to nitrogen atoms, and so on and so forth. So these are some of the things that you take note of as you are doing molecular modeling. All right, and also besides that, we also have issues to do with like bond length. All right, so between this carbon atom and the other carbon atom, you need to know like how the length of this bond that you are making. So basically, that's what we're dealing with molecular modeling, even as we try to make a 3D structure from a 2D structure. And this is an example of what it is. So here, when we talked of ChemDraw, we said we are making a 3D structure, or sorry, a 2D structure. So this is a 2D structure that you have made from your ChemDraw. But this structure can be converted to a 3D structure using molecular modeling applications. And this is how it would look like. So issues with 3D structures, it helps you come up, visualize how this compound would look like in space. All right, so it gives you that clear picture. So with the ChemDraw, it's just like a 2D structure. You can't really see how the orientation of these different atoms in space. But with a 3D structure, it would give you a proper orientation of these different atoms in space. All right, and even as you are studying your compound, it's easier for you to visualize it when it's in 3D structure, and that is one of the importance of using these different softwares. Okay. Somebody's saying I'm low again. I'm so sorry. Oh God, I'm in the office and I don't want to make noise for the others, but then I'll try to speak louder. Okay, so this is what it is with a 3D structure. Okay, and so as we are making this 3D structure from a 2D structure, there are certain things that there are certain changes that can occur from your original 2D structure to a 3D structure, okay, when you're using this software. So because of those changes that can occur, there's what we call energy minimization. With energy minimization, we are saying once you have formed this 3D structure from a 2D structure, there are certain changes that will occur, changes in the bond length. You know, we did talk about you have to take that we need to take note of the bond length. Okay, so there are going to be changes in the bond length. There are going to be changes in the bond angles and torsion angles. So because of those changes that will occur as you are drawing a 3D structure from a 2D structure, you need to apply what we call energy minimization to kind of work out those changes that are going to occur. All right. So this energy minimization that we have talked about, we've said that once you have made this new 3D structure, okay, you find that sometimes it will be, how do I say it? So you have maybe let's say your starting compound was kind of maybe it was actually more stable than the one that you have formed at the second time, like the 3D structure. So we are saying we are trying to apply energy minimization concept so that you try and overcome all these changes that I've mentioned, like bond length, bond angle, torsion angle, so that you stabilize your compound. You don't want it to be unstable. You want it to be very stable. So energy minimization is helping out to stabilize the compound that um, the compound that you have made. All right, and yeah, so that's basically what it is. And so for the software, it will actually notice to say uh, there has been some changes in bond length, there have been some changes in bond angles, torsion angles. The software is able to see those changes and able to fix all of them so that you have a stable compound. All right. And this is just an example. This is like to show you how these changes of on energy minimization will work out. But there's also another component later on where I'll show you more about energy minimization. But basically, at this position, let's say this is your starting compound. All right. And you find that after you've done this energy minimization, by the time it's reaching at this stage, it would have been uh, stabilized as compared to how it was at that position. Okay, I'll explain more later on. Okay, so that's with the use of this software. So we've mentioned that you can use it for drawing these chemical structures. You can use computers in coming up with a use of molecular modeling, where we've talked of changing the 2D structures to 3D structures so that you can be able to visualize them well and be able to yeah, study your compounds well and see how they can be in space. All right. So the other one is the viewing of 3D molecules. So like we have mentioned that you can you can make a 3D molecule using these structures, and then you actually after that you can now do energy minimization so that your compound can be now stable. All right. So after that, now you can now view your molecule. Okay, so you can rotate it at different positions. So depending on the compound that you have designed, the compound is going to have this we've talked of different bond lengths, bond angles, and there are these bonds that are rotatable. All right. So there are those bonds that can easily rotate. So meaning that you can move around your 3D molecule. Too bad we can't visualize it here, but it's interesting when you are using the software. You can actually see you can rotate your compound in different positions, and you'll be able to see the different positions of your molecule. And besides that, also with the use of these softwares, you can have the 3D structures can be visualized in different forms. You've got forms that we call like cylindrical bonds. It will give you wireframes, ball and stick, space filling, and so on and so forth. These are different formats of how your 3D structures can be visualized as you are studying them. Then the other way is the use of ribbon format. So ribbon format is another format that can be utilized as you are trying to study this 3D structure. And this one is mostly used when you're looking at proteins. All right. So with the use of ribbon format, it allows you to see these complex structures like proteins. Okay. I hope I have something. Okay. So this is the ball and stick um, visualization of your compound. So you can have it in this way. All right, so this should be 1, 2, 3, 4, 5, 6. This is a benzene. All right. So instead of having just benzene, then the normal way we have it, the way we draw, so it can be visualized in this form as a ball and stick, and you'll be able to rotate it in different orientations. Then it can be also in this format where we call a space filling format of the 3D structure. And then you also have the wireframe. Okay, so you can also have this uh, visualization. You can view your structure in this form. And then this is the ribbon format. So with the ribbon format, like I've mentioned, it's mostly useful when you are looking at proteins, the complex structures of proteins. So for this one, unfortunately, I didn't add different one, but what you notice that at this position, I can even have like a ligand. You know, a protein is acting, let's say, as a receptor, or an enzyme, or as a target molecule. So once you have your ligand, like let's say your different drug molecule, you can actually have it, let's say it's bound at this position here. So you can study how your compound or your drug is bound to this protein structure with the use of these 3D these different softwares. All right, and you'll be able to rotate and see what amino acids are here on your proteins where your drug is bound. Okay. All right, so that's with viewing the 3D, the use of computer softwares in viewing the 3D structures. And then besides that, there's also, yeah, like this is what I talked about. When you're talking of like these softwares, uh, mm, they can also help you to identify these different angles that we've talked of. We talked of the bond length, bond angles, in the dihedral angles. Dihedral angles are the same as torsion angles. All right. So with the use of these softwares, you can actually see uh, the the angle of these bonds that are forming in your compound, and also the length. So you notice to say if there's an issue with a certain bond length and bond angles, this can be worked on with the use of things like energy minimization processes. Okay, so with the use of these same 3D structures that you may have constructed using molecular modeling, you are able to, the software is able to give you molecular properties, okay, properties to do with like steric energy. All right, so with steric energy, it's also trying to it's trying to help you. It's trying to give you information on the strain, okay, the strain that this molecule is undergoing. You know, so you find that it will give you information on, let's say, to tell you that there's so much strain in this compound that you have made. Okay, so that information will be shown on the softwares that you are using. Okay, and once it gives you that information to say there is so much strain here, you can now apply your energy minimization so that the strain that has been given there can be worked on. Okay, the other molecular properties that can come will be bond stretching or deformed bond angles. Let's say the bond angle that you needed was between atoms was, let's say, 120 degrees. And once you have made your 3D structure, you find that maybe the bond has reduced to 60, 90 degrees. So that information will be shown to you. And because of that, you can apply these uh, applications like energy minimization to help out in correcting those deformed bond angles. And bond stretching, you know, like the bond has become longer than the required, like let's say for bond length, maybe you wanted about 1.42, then you find that you've made about 1.67. That information can be seen, and something that can be worked on using these softwares. And the other interesting properties that are seen are partial charges. Okay, so with partial charges, what we mean is that like for us when we are drawing, let's say different compounds, let's say a group, okay, you are drawing, let's say your ammonia, NH4 plus. Okay, for us when we are writing, we'd always put maybe plus at our nitrogen atom or so on and so forth. Anyway, like these electrons or the charges, we'll put them like we feel as if they are supposed to be fixed at a certain position. But with the use of these computer softwares, you actually find that these, let's say the valence electrons, sorry, are not fixed at a particular atom, but rather they occupy a specific region of a compound or a group. So I'm going to show you something later on. So let's say in a case for like about, let's say electronegative atoms, we'll find that electronegative atoms like oxygen, you notice to say when we are drawing, we always want write as if the electrons are just localized at that electronegative atom like oxygen. But what the softwares will show you will be that they are not actually localized, but rather they are in a specific region of these different compounds. Okay, and this is somewhere, okay, here. All right, so this is an example of what it is. Besides that, let me see. Do I have it? Okay, it's there. All right, so this is an example of histamine structure. So for us, we would normally draw it like that and put a positive charge there at nitrogen atom. All right, thinking that the charge is just localized at that nitrogen atom. Okay, or even when we are trying to, let's say, imagine how our histamine is going to is going to bind to the histamine receptors. For us, we are going to make it seem as if the interaction of this ionic interaction that is going to occur between our histamine and our histamine receptor is only going to occur at that specific nitrogen atom, of which that is not the case. So with the use of these softwares, you're going to find that it will show you that the partial charges are actually not localized on a specific atom, but rather diffuse in a specific region. And this is what it is at this atom, at this structure, sorry. So for us, our prediction would feel as if the interaction will occur like at the binding site. All right, at our binding site, let's say we have got this group here, and then we have our group on the drug. Okay, like our histamine, we said there's a positive charge there. So we feel as if an interaction will just be specific at the nitrogen atom and the carbonyl compound there, of which is not the case, the carbonyl group, all right, of which is not the case. The case would be that this positive charge, which is on the nitrogen atom, is actually diffuse. It's occupying a specific region of the compound. The same thing is applying to the binding site. At the binding site also, the negative charge that we saw here is not localized on oxygen atom, but rather it's occupying a specific region of the binding site. So this is the interaction that you are supposed to, that you can visualize with the use of these softwares. So it kind of gives you a more clear picture on how your compound or your drug molecule is going to interact with your binding site, because it's going to give you how how diffuse these electrons are on your compound. Okay, so that's with those ones. So do we have any questions? Because I will be logged out in 4 minutes time. So before I start the other component for conformation analysis, can I get any questions from the previous, from what we have discussed so far? Do we have any questions before we are logged out and continue with the other part? Are we together? Anita, are you following?
Yes, madam, we are.
Okay. All right. Okay, that's good. Okay. So the rest of you, who else is here?
Sorry, madam, me, I didn't follow on energy.
On which one? Yes, Roida. On which one? Roida, you are saying?
On energy minimization.
Sorry, Roida, you are cutting. You're not so audible.
I didn't quite follow the concept of energy minimization.
Okay, no, you understand it later on, like there's another point where I'm going to
Okay, let me
explain.
take.
All right, I'm going to explain well in the next slides. I explained it better on another concept under energy minimization. So I'm sure you understand it later. And Kennedy, you have your hand up.
Yes, madam.
Yes.
I just wanted to ask or confirm which software are we using to consider the partial atomic charges on the molecules?
Oh, for this one, it's molecular modeling.
Molecular modeling.
Yes, it's not really a software. Molecular modeling is not a software, but it's how do I say? Like an application, sort of. It's not like it's there as it's like a concept, or it's like a concept, but that's not a software. Okay, so like you have different softwares, like I don't have it, but there's is it 3D Chem or something like that. I need to check it out, but it should be a 3D Chem. Yeah. So it's not we are utilizing a concept of molecular modeling, okay, but not a software. Yes, it's a concept of molecular modeling that we are talking about, but not a software. Yeah, the software should be. Let me just take that because I don't have it on my laptop because I need to buy. I think I didn't even write it down, but it should be. No, I didn't write it down. But it's something. It should be a 3D ChemDraw, if I'm not mistaken. The only software that I have at the moment is ChemDraw software. I don't have the one for 3D yet. I need to buy it. Yeah, it's Chem 3D. It's a Chem 3D software. That's the one that helps out with molecular modeling applications. All right, so we are going to log out now, so we can log in with the same login password that I gave you. All right, let me just end the meeting. Your maybe oxygen on this other part of the molecule and oxygen on the other part of the molecule. Maybe oxygen will be more comfortable to be next to a part of the molecule that has got a hydrogen atom, so that you can have that hydrogen bonding, or maybe oxygen or maybe a nitrogen atom that has got a positive charge, okay, would want to be next to a oxygen atom that has got a negative charge, so that they can have that interaction. But when you force it to be next to another part of the molecule that is also positive charge, you are increasing on the strain of this molecule. Hence, the conformation of that molecule is going to be highly strained, meaning the molecule, the compound in that conformation is unstable. But what you want, therefore, is that you want your molecules to be, or your compound to be in a conformation or a position where the strain is not so much. And having said that, this was just a by the way thing that I had put across, which is talking of issues with the Newman projection. All right, with Newman projection, I've put this part here because I want you to understand how these different compounds can be in space. So I will take you to this one. This is the important part that I just wanted us to get when you talk of this Newman projection. So with the different, like we are saying they'll have different conformation these compounds will have different conformation, or the parts of the molecules have different conformation. An example is for this compound. All right, this is the same compound, but it can be in a conformation that we call anti-conformation and gauge conformation. All right, so on top here, where I'm pointing here, there's a carbon atom, and then that circle behind also, it's representing another carbon atom. So this carbon atom is in front, connected to a carbon atom which is behind. So try to visualize that in space. All right, so I've got a carbon atom here, which is here in front of you. Then you've got another, which is bonded to another carbon, that circle behind, which is behind. And then the carbon which is behind there on the circle, it's bonded to a CH3 at that position. Then this carbon which is here in front of you is bonded to another CH3. All right. So with this conformation of this molecule, the distance between these two substituents, this carbon methyl group, sorry, CH3 here, and the other CH3, the angle between them is like 180 degrees. All right. So that means that they are quite far from each other. And because of that, you are trying to reduce on the strain of this compound. Right. So now compare this one to the other conformation here, which is the gauge conformation. So the gauge conformation, the same molecule, right? We've said it's the same molecule having the same atoms and the same bonds. But now here you have this carbon atom, this CH3 is bonded at an angle. In comparing this CH3 here and the other CH3, the distance between them is like 60 degrees apart. Because of that, you find that the this gauge conformation of this molecule is more strained compared to the other one. Why? Because of the distance between the two substituents that are there. So this is what it is when I'm talking about these different conformations of the different compounds or molecules in space. So you find that this the gauge conformation of this compound is more strained than the anti-conformation, and this one has got high energy. This one, the one which is unstable, than this one which is stable. So even when it comes to energy minimization, if you find that you have got you have made, like using the use of molecular modeling, found a gauge conformation which is like this, and 60 degrees apart, you find that this is not very, it's unstable. So you may apply these applications so that you change the conformation to the anti-conformation so that you try to minimize the energy. So this is where issues of energy minimization would apply. So the change of conformation from this conformation to the other one will help out in energy minimization. So you're minimizing the energy, the strain, which is there, the steric hindrance, the steric energy, which is in gauge. You are reducing it by changing the conformation of this compound from this conformation to the other one. Okay. And yeah, just continuing from that. Okay. The same issues with energy minimization. There's what we call the local and global energy minima. Okay, so we have that 3D structure. Okay, like I've mentioned from the previous gauge and anti-conformation, you have this 3D structure. All right, and then once you have you have drawn this 3D structure, let's say with the use of your Chem 3D software, you have the 3D structure, and then you now want to, after you have made that 3D structure, after you have drawn that 3D structure, you want it to be stable. You want it to have a stable conformation, all right? Not to be unstable. And because of that, you apply energy minimization. It's also an application, you know, of this software. You apply it so that the computer software should be able to work on this 3D conformation that you have made to try and stabilize it by changing the conformation. In a case that it was a gauge one, it may change it to the anti-conformation so that it's it's stable. All right, and then, but the catch is that with energy minimization software, or just a quick one, just a minute, I have an important call, just a minute, I'll get back. So let's continue. So like I was mentioning, with energy minimization, there's something that we need to take note of. So there's what we call local and global energy minima. So once we have your 3D structure, and after you have made your 3D structure, you need to, the next thing that you need to do is to apply energy minimization, all right? And why are you applying that? Is because you want your 3D structure to occupy a stable conformation. But then there's something that is interesting, is that with energy minimization, you are not assured to obtain the most stable conformation of your compound. And why is that? It's because with energy minimization concept or software application, what happens is that with energy minimization concept, the compound that you made will reach a certain barrier that it cannot overcome. Okay, this is the software. It will reach a certain barrier which it will not overcome. Hence, it will stop making different conformations of your compound. You know, let's say instead of making 10 conformations, all right? So if the 10th conformation was going to be the most stable conformation, you find that your software maybe will only end at maybe the 5th conformation, all right? So it ends at the 5th conformation because it's going to find what we call a saddle, a barrier, which it will not overcome. And it will not, it's a software, so it will not know to say, after overcoming this software, this barrier, there are other more stable conformations that the software can attain at maybe position 10. So this is what happens with it, local and energy minima. I'm going to explain to you in a graph, okay, here. So this is a starting structure. So your 3D structure, once you have had it, then now you apply energy minimization. You find that there's a first step which we call a local energy minima. This is where your compound will end. Like after it's doing this, after the application of energy minimization, the software will end here. Okay, it will end here because there is a saddle here that we talk about as kind of a barrier. All right. So this software will not know to say after this barrier, there's actually a point which you call a global energy minimum, where you can obtain the most stable conformation of your compound. So meaning the compound that you're going to obtain here will only have attained stabilization until this point and not up to the other end. So you're not going to have the most stable conformation, the one you can apply, you can get at this position, but rather you're going to get them kind of a less stable conformation of your compound at that state. So that's how energy minimization is coming in. It's helping you to, after you have drawn your 3D structure, it's helping you to attain a stable conformation of your 3D structure, so that you kind of reduce on the strain, the steric energy that can occur. You know, you're trying to work on all that with this application. All right. And yeah, this is what I've talked about all this. The first stable conformation, which you can, is what you apply, you get at local energy minimization, which is now have a barrier where you cannot obtain the most stable conformation. I've explained all this. So what it is that that's a limitation with energy minimization, you know, program, which is you cannot obtain the most stable conformation of your structure because of the presence of that barrier, the NH saddle, which is here. So because of that, you find that there are other methods. You know, we did talk about trying to analyze the conformation of compounds. So there are other methods that come in that can help identify the most stable conformations. And these are the molecular dynamics and stepwise rotation of bonds. I did talk about them at the beginning, and Monte Carlos, but I've only picked two. That's molecular dynamics and stepwise rotation of bonds. So these two programs are going to help us to identify the most stable conformations, which cannot be identified with the energy minimization program. So with molecular dynamics program, where it's designed, this program is designed to try and mimic, okay, it's trying to mimic the movement of atoms within a molecule. So you have a molecule, or you have your compound, okay, you have your benzene, you have your histamine, and so on and so forth. So with the molecular dynamics software or program, it's trying to show, to mimic how the actual atoms are able to move within the molecule, okay? And because of that, this program will kind of visualize this, the structure, okay, as moving spheres. So I've got these spheres like circles. It views these atoms as circles that are moving, okay, because we are saying the movement of atoms is mimicking the movement of atoms in a molecule, and these atoms are visualized as spheres. So you have got oxygen as an atom, it's seen as a sphere, as a circle. All right, you have got hydrogen. So this program is designed to see that hydrogen atom as a sphere which is moving. All right, so because of that, now we are saying that with after some femtoseconds, that's 1 times 10 to the power negative 15 of seconds of movement. So after these femtoseconds, after these atoms have moved, these spheres have moved for about a femtosecond, the position and the velocity of each atom is identified or determined. So you have got your benzene, okay? Benzene has got C bonded to another C, bonded to H, and so on and so forth. So after the movement of, after we are saying that each atom is moving, okay? Your carbon atom is moving, your hydrogen atom is moving. So after each of these atoms has moved for about a femtosecond, the position, okay, of this atom, the velocity of each of this atom is identified, or is determined or calculated. All right, and also besides that, you also have issues of potential energy is also calculated. You are also going to look at the bond length. You're going to look at your bond angles. So if let's say you have your benzene, okay, I'll keep going back to benzene, your carbon atoms, your hydrogen atoms, after femtoseconds, that sphere of hydrogen atom, the carbon atom, after it has moved from this position to the next position, you need to determine the velocity. You need to determine the potential energy by looking at the bond length. Has there been any changes in the bond length? Have there been any changes in the molecule, in the bond angles after this compound or molecule has moved from position A to position B? That's what this software is doing, okay? And how is this movement occurring? Because we are saying the software is mimicking the movement of atoms in the molecule, but how is this this thing being done? It's being done by the software is designed in such a way that it's the molecule or the compound is exposed, is exposed to heat. Okay, so the molecule is exposed to heat. All right, that's about 900 K. So the molecule is exposed to heat. Okay, so after each femtosecond, these atoms are moving after being exposed to this heat. They are moving from one position to the others. And then because of that movement, we are saying there are changes, and because of being exposed to this source of heat, you know, they are changing their in bond strength, bond rotation, and so on and so forth. There are all those changes. And then because of that, you find that with this application of molecular dynamics, the way this software is designed, it's actually able to overcome the energy barriers. The energy barriers are the one, like an example of an energy barrier is that energy which we saw in energy minimization here, the energy saddle, right? So with this molecular dynamics, unlike energy minimization program, this molecular dynamic is able to overcome this energy saddle, which is between two different conformations of the compound. Why? Because of the presence of, because of this, the way it is designed to being exposed to heat. Okay, so like after you've exposed this molecule to 900 K, then you need to allow it to cool to about 300 K. Then after you have cooled that that compound, that's when you can have now the final structure. At that time, we believe to say you would have overcome the energy saddle, hence obtained the most stable conformation of your molecule or the compound. So this process can actually be repeated several times. So as you keep repeating this process, you'll find that you can even have different structures, okay, different conformations of the compound, and then or different structures. And you have, let's say, if you're working on a group of different lead compounds, okay, you have one compound. Listen, this is a lead compound. Maybe you are doing, we talked of issues to do with unique combinatorial synthesis. You have made all these, let's say 10 compounds, okay? You've made your 10 compounds, and then you also find that after you've made your 10 compounds, the 10 structures, you can apply molecular dynamics to each and every one of these 10 structures so that you have different types of conformations for each of them. Okay, you can have different conformations. Can we please mute our mics? So you can have different conformations for all these different structures, and then you can even compare them and see which one would be easier for you to actually synthesize in the laboratory. Okay, that's with molecular dynamics. So this is just an example of what can happen. So once, let's say you've created your ChemDraw, you have you've made this, you've drawn this structure in using your ChemDraw, then you import it in your Chem3D. Chem3D, we said it can help you come up with a 3D structure of your compound, the conformation. So after you apply 3D software, you can, let's say, have a gauge conformation of this structure. After you have your gauge conformation, you are saying, no, but this angle, remember what I explained before, this angle is like 60 degrees. So meaning this compound is very strained in this conformation. Hence, you'd want it to be, to have a better conformation where the bond angle is kind of longer so that it's not so strained. So you can apply molecular dynamics, okay, software or program, so that it can help you obtain a more stable conformation of your structure. And in this case, even an anti-conformation can be applied with a longer angle, like 180 degrees angle. Okay, okay, this, I've explained all this in the structure. All right, that's with molecular dynamics. Okay, so you've got molecular dynamics program would help you to analyze the conformation of your structure to help you to identify the more stable conformation of your structure, so that, yeah, because what you want to have is, you'd want to have the most stable conformation of your compound. So with molecular dynamics can be applied and to help you obtain that stable conformation. So the second conformation analysis program that can be used is a stepwise bond rotation. So again, molecular dynamics program that will not guarantee to identify all the possible conformations of the structure. You know, it's important to have, like once you have drawn this structure, it's important for you to have different conformations of one structure or mole or compound, because you need to compare all these structures to see which one will be most stable. You know, it would help you, that is kind of better to have a variety of conformations and like only having a few of them. So with molecular dynamics, it will not really give you all the possible conformations of the structure. But with stepwise bond rotation, it will actually give you a lot of a variety of different conformations of the structure. And with this one, how is it done? The stepwise bond rotation. Unlike molecular dynamics, where we're applying heat, visualizing the movement of atoms and all that, with this one, it utilizes the use of rotation. Okay, it helps with rotation of each and every single bond in your structure. Okay, so you're going to rotate each and every bond, but anyway, not all the bonds are rotatable, but all those bonds that are able to rotate, you need to rotate each and every one of them so that you have a variety of or a variety of structures or different conformations. So unlike so with stepwise bond rotation, actually for this one, energy minimization is not even carried out. Why is that? For stepwise bond rotation, our main aim of using this program is not to obtain it's for our main aim of use of this stepwise bond rotation is to identify both the stable and the unstable conformation of your compound, so that you can now come and look at them and study both of them, right? And so with these softwares, you find that they can actually identify which of the bonds are able to rotate and which ones are not able to rotate, because certain angles will not be able to rotate. All right. So bonds like hydrogen, so like atoms bonded to hydrogen atoms, okay? Let's say carbon bonded to hydrogen atom, that bond will not be able to rotate, okay? Let's say carbon, another bonds bonded, connected to methyl groups. These ones are also excluded because these ones will not really form, like after you have made your conformations, rotating these kind of bonds will not really be significant. So you can actually exclude them as you are trying to determine which bonds you have to rotate for you to come up with different conformations. Okay, so like I mentioned, with stepwise bond rotation program, you can actually have a lot of different conformations, even up to 1,000 can be made. And then you just have to now compare and see which one of them is the one you would want to go with and exclude others. All right. Let's see. All right, that's really basically what it is with stepwise rotation. And again, we are running out of time. When you have like 3 minutes before we are logged out. So when you log out, you can join in one more time. Okay, so we have another concept of use of our computers in Medchem, where you can use them to identify the active conformation. So what it is that we have mentioned that your compound can have different conformation or different orientation in space, the 3D structures, but not all those. Let's say we kept talking about the stable ones, okay? We keep saying the stable conformation, but that doesn't necessarily mean that your stable conformation of the compound will actually be the active conformation, okay? So the active conformation, you want to identify with the active conformation, we are saying this is a conformation of the position of the structure that is able to fit well, okay, to fit well within the target binding site and be able to maybe produce your activity, okay. But again, the active conformation can either be stable or less stable conformations. It's not automatic, but the most stable conformations will be the active conformations. All right. And then, so with that, identifying the active conformation of these different conformations that you have made, we have got methods that are used. We've got X-ray crystallography, and we have comparing of rigid and non-rigid ligands. These are the methods that are used in identifying the active conformation. All right, so be logged out now. Then you can join in again to see how far we can go with the lecture. Okay. Okay, we don't have enough time, so I'll keep talking as I'm trying to add your friends. So I've clicked on record. You can record and share with your friends who are unable to join. Okay, so we've mentioned what active conformations are. Okay, so we are saying we have all these. You can have all these number of different conformations, but not all of them are going to be active conformations. That is, active conformations, this is the specific position or shape of a molecule that will be able to fit in the specific target binding site. All right, so but then how can you identify which of your different conformation is the active conformation? So with the use of X-ray crystallography and the comparing of the rigid to the non-rigid ligands, you are able to identify the active conformation. So with X-ray crystallography, expect you guys to understand what it is, because this is where we looked at that assignment that I gave you. So with X-ray crystallography, what it is that you have all these different libraries on the internet, like what do they call them? Yeah, they call them libraries, where you have what we call, you can also call them like protein bank data banks or libraries, where you can find different proteins that have been crystallized. Okay, not all proteins are able to be crystallized, but most of them are. So the crystallized proteins in these databases, you can have them, you can get these proteins, and also sometimes you can find a complex of protein which is bound to a ligand, the complex. So you're able to, with the use of X-ray crystallography, you are now able to study that complex, you know, because you have your target, which is the protein. You have got your ligand, which is maybe the drug structure or drug compound. So you can look at that information on your computers and try and analyze how that ligand is bound to this protein. In what orientation is it? What substituents of the structure or your ligand or your drug compound are bound to the protein? What part of the protein or what part of these amino acids are bound to this ligand? So this is how X-ray crystallography comes in to help in identifying the active conformation. It is actually, I think, the easiest way, because you can just look at the ligand and see which part of the ligand, how is this ligand bound to this protein. It will give you a specific orientation, and that's how you can be able to, and that's how you can be able to, can we please mute our mics? And that's how you can be able to identify which of these conformation is your the active one. So let me repeat on this one. So you have, let's say you have this, you have your, which drug? You have your drug A, okay? Drug A that you have made now. Okay, you have drug B today. Drug A was made a long time ago, and it has been crystallized and it's in the database. Okay, that was drug A. Okay, and then because it's in the database, that drug A was made by someone and they've crystallized it. That structure has been crystallized together with its target molecule, like a protein. It has been crystallized. So you can download that complex of protein with your structure A, and then see how that structure A is bound to that protein. Okay, you're going to look at the functional groups and how are they in space? How is this structure A in space? How is it bound? You're going to, by studying how structure A is bound to the protein, when you're looking at your structure B, the one that you are working on now, when you look at it, after you've done this energy minimization or molecular dynamic softwares, and you have these different conformations, you're going to look at those conformations of your structure B and compare which of those conformation of your structure B is it related, which one of them is similar to that of compound A, which is in the database in terms of conformation, and that's how you're going to pick which of your 10 conformations of your structure B is the active one. So that's with X-ray crystallography. Then, besides that, also we have what we call like the 3D pharmacophore identification. Okay, so we also need to identify the pharmacophore. We know pharmacophore. This is the part of the molecule that is able to interact with the target site and be able to produce the desired activity that you want. Okay, so with the pharmacophore identification, there's the 3D identification. So with this one, you are able to visualize the position of the important binding groups. Okay, the important binding groups that are there on your ligand. Okay, and how they are bound to the important binding groups of your ligand as you try to relate them to the binding site. So with a 3D one, you're able to visualize those important binding groups in space. Okay, but as you are visualizing them, you get rid of the molecular skeleton. Okay, so let's say you have a compound like a benzene ring connected to hydroxyl OH, the other one connected to CH3. Then once you identify that the important part of this benzene ring connected to hydroxyl to CH3 is the CH3 and hydroxyl group, then you can get rid of the molecular skeleton, which is the benzene, so that you don't look at it. You get rid of it using this software, like you delete it, then you remain with your CH3 and then the hydroxyl group, and that would help you to visualize as you try to identify the pharmacophore. Okay, I'll explain later more in details for you to understand. So what it is that with these, as you are trying to identify the pharmacophore of these different structures, again, you are able to utilize X-ray crystallography and what we call structure comparison of active compounds and the automatic identification of pharmacophore. So these are the different methods that are utilized. All right, so let's go in details on how you can identify your pharmacophore on the 3D one. Okay, with this X-ray crystallography, I've explained a bit when you're trying to identify the active conformation. It's kind of similar as you are also trying to identify the pharmacophore. I've explained about how you look at the crystals. Okay, here I'm just explaining how crystals are formed. It's not really that important. You can start from here. Okay, so that's X-ray crystallography. So this technique, okay, it's helping you to determine the atoms and them it's helping to determine the atomic and the molecular structure of the crystal. So you have crystallized this, your ligand or your compound. You've also crystallized your target molecule, like your protein. Okay, so what it is that I've already mentioned to say this protein ligand complex can be downloaded on your computer. Once you download, then you are able to now study you know, like which part of your ligand is interacting with the molecule, the protein, which bonds are interacting, what interactions are there. Do you have hydrogen interactions? Is there hydrogen bond acceptors? Do you have van der Waals interactions occurring? So that is what you have to do as you are studying and trying to identify the pharmacophore, okay? And then besides that also, we also have to deal with measuring of the distance, okay? That the distance that is between the binding groups, okay? You have to identify the distance that is there between the binding groups that are there in your molecule and or your ligand, and the molecules that are the atoms that are found there in your binding site. You need also to try and look at the distance that is there. So once you identify the binding groups, okay, you have your crystal ligand and your protein. Once you identify which of these groups are binding to each other, once you identify that, you now need to note the position of those binding groups. Let's say there's hydroxyl group, carbonyl, there's methyl, aromatic rings. You need to identify which of those groups are binding between your ligand and your target binding site. So once you identify those ones, the position of those binding groups should be mapped. Okay, so you have to mark them or map them so that it can help you to produce the pharmacophore. All right, so that's how you identify the pharmacophore. You look at the structure, the complex between your ligand and your protein. See what groups are binding in between the ligand and the protein. And once you identify those groups, map those groups or mark them, then you'll be able to understand the pharmacophore to say, okay, actually, if I have to make an analog of this ligand, which is in the protein database, I have to, the drug that I'm going to make should have hydroxyl group, should have a methyl group at that position, so on and so forth. And that's what is done. Then the other method of identifying the 3D pharmacophore is by use of structure comparison of active compounds. Okay, in this case, what we are saying that there are situations where the structure of the target protein or what is not known, okay? But now you want to, but you still, unlike use of X-ray crystallograph where you had the structure of the protein known and the ligand known. In this case, you may not know the structure of the target molecule, okay? You only know the structure of your ligand, but how then can you identify the pharmacophore, okay? So you can identify the 3D pharmacophore by use of, by looking at a range of different active compounds, okay? So in a case that you have got, let's say different compounds, you have these different, an example, maybe these beta-1, what are these? Beta-1 blockers, like you have what are these? Carvedilo, whatever, these low, atenelo, and all those ones. So you have got, let's say you have got a class of many different active compounds, okay? An example would be, let's say the same beta-1 antagonists, blockers or antagonists, you have them, all right? And amongst these compounds that you have, you may have one compound, which is a rigid molecule, okay? By rigid, we mean that that molecule only has one conformation, meaning it cannot be put in different conformations. So you need to take note of that, that active. Let's say you have enalapril, carvedilo, atenelo, what other laws? Anyone to remember one? I've forgotten. Atenelo, carvedilo, which other ones?
Propranolol.
Yes, those ones. Okay, so I've got the three of them. You have atenolol, propranolol, carvedilo. And an example, maybe we have, let's say your propranolol is the only rigid molecule, meaning propranolol is the only one which can be found in one conformation. So you can start by and yet you don't know the pharmacophore of this class of drugs. So you can start by identifying the pharmacophore of the rigid one, which is propranolol, before you look at atenolol and carvedilol. And how can that be done? Okay, so once you identify the geometry of this, the pharmacophore of this rigid molecule, then you can overlay the other active compounds. You can overlay them on top of propranolol for you to be able to identify which of these ones are matching. Okay, so meaning if those are matching, then those are the pharmacophores. Those are the important groups that should be there for your compound to be able to produce the desired effect. And that can be seen here. All right, an example is between procaine and cocaine. If you don't know the pharmacophore of these drugs, but they are falling in the same class, you can, an example that was used was, which one was rigid? This one should be rigid, I think. Yes, this one is a rigid one. Cocaine is rigid. So if you have to find the pharmacophore of the two, you can overlay this procaine on top of cocaine. So as you can see here, this one, procaine has been overlaid on top of cocaine. And because of that, then you can be able to identify the similarities of the groups. So like here, we can notice that no, there's actually aromatic ring, there are these carbonyl groups, and so on and so forth. So with that, you'll be able to have an idea of how the pharmacophore should look like, even though you don't know the structure of the binding site. So that's one concept. Then the other way of identifying the pharmacophore would be where you use automatic identification of pharmacophore. So all these things, we are using computers and softwares. So automatic identification of pharmacophore, how can this be done? We're saying a 3D pharmacophore of these different active compounds can be identified when you, even when you don't know the important binding groups. How can that be done? The first thing that you have to do with this automatic identification program is that you need to identify, or the program or software identifies the potential binding centers in the molecule. What are those things? So when you're looking at these different compounds, there are these important common binding centers that you can just approximate by looking at the molecule. So those ones that you need to take note of, the binding centers, like the software would also take note of, are the hydrogen bond donors. To identify the hydrogen bond donors, hydrogen bond receptors, it would identify the aromatic rings, it will identify the acidic and the basic groups. So it's going to identify these groups, and also besides that, it can also identifies the hydrophobic centers. These carbon molecules, like carbon atoms more than 3, and so on and so forth. So once it identifies these things, an example that I've put is for dopamine. This is a dopamine structure. So if the program is working on this structure, it will first of all identify the potential binding centers. It will look at this amine group there, hydroxyl group there, another hydroxyl group there, and the hydrophobic center, which is the aromatic group. All right, so what happens after identifying that? The second thing that you will do is that the software will now identify the various triangles. Okay, it will make triangles which connects these important centers. So here the first thing, it identifies the important binding centers. The next thing it will do, it will make triangles that connect these important centers. In an example was like for dopamine. Dopamine, we did say that it has 2 phenolic groups, 1, 2, 3 amino group, and it has got a aromatic ring. So with dopamine, you find that it can even have about 4 triangles are going to be identified. That is, each possible binding center will produce a triangle. Okay. So after these triangles have been identified by use this program, then the stepwise bond rotation. Remember we talked about stepwise bond rotation program is now going to be applied. This one is applied. Why? Because you want it to be able to generate a range of different conformations. Okay, so it will arrange a range of different conformations, whereby, because you need to compare, even after you've identified the possible, these triangles have been identified, okay, of possible binding centers, because they're trying to come up with a pharmacophore, but pharmacophore can be also in different conformations. So meaning you need to apply this stepwise bond rotation so that you have different conformations of your pharmacophore. All right. So once you have these different pharmacophore, then what happens next would be okay. So what happens next would be for you to let me see this one. I was given an example of dopamine. Let me see that we can. Okay, in a case of, because I was trying to explain for you to understand in the case of dopamine. Okay, so in the case of dopamine, we said four triangles are identified. Those 4 triangles are representing the 4 possible binding centers. Okay, so once you do that, then you apply stepwise bond rotation. A stepwise bond rotation will produce many different triangles or many different conformations of the pharmacophore. After that, you add up all those triangles to give a number, a total number of possible conformation triangles, or the different conformations of dopamine. Okay, and then after that, then if you have to, if you are trying to get now, you can now look at another compound that has got similar activity to dopamine, because dopamine, you have identified the binding centers, you have identified the triangles and the different conformations. What next do you do? Is by picking another structure or compound that has got similar activity to that of dopamine. So once you identify that one also, what you do next is that you now have to compare, okay? You also have to look at, when you look at the structure or a compound with similar activity as dopamine, you also need to identify the pharmacophore, the possible binding centers of that other structure. Also make the pharmacophore triangles. After that, then you need to compare these two. This new structure, you compare it to dopamine. Okay. Then once you compare it, the pharmacophore, you now have to identify which of these pharmacophore triangles are similar. Okay. With the one for dopamine, you compare them to another compound that has got similar activity. So you compare them and identify the common pharmacophore that are found in both structures. After that, then you can do what we call plotting, a 3D plot, for you to just give you a visual display, all right? It's just helping you to identify in what location these triangles or these binding centers are, okay? And just helping you to identify them. So this is what it is, okay? You have got your dopamine there. The first thing we did was to identify the possible binding centers. We have the hydroxyl groups there. We have the aromatic ring. Can you please mute? We have also the amino group there. So after that, please let's mute our mics. After that, then for you to visualize it well and identify the pharmacophore, you need to remove the skeleton. So you remove all of these. All right. So you remove the skeleton and just remain with those 4 dots, okay? Those ones. So you now make triangles on each of them for you to identify pharmacophore triangles, which are now put together. We did identify 4 of them are there for dopamine, okay? And then, like I mentioned, now you need to look at another structure that has got similar activity like dopamine, then compare the triangles and then the Pharmacophore plot. This is how it looks like. Okay, that's with that one, identification. Okay, now there's one procedure that we call docking procedure. Okay, so with docking, what it is, you're just trying to, it's a study, okay, that is used to identify how two or more molecular structures of a drug, okay, and receptor can match up to make a perfect fit. Okay, so you're trying to study how this your drug or your ligand is able to make a perfect fit or able to bind well to this binding site like a receptor. So these procedures, we have got what we call manual docking, and then there's automatic docking. So with manual docking, with the molecular modeling application concept, it can be used in this docking or fit a molecule or fitting a molecule into its binding site. So how is this done? The manual docking, docking, we're just saying we're trying to fit your ligand into your binding site. How can this be done manually? How it can be done is that you, as the one operating the computer and all that, you have to identify which ones are the binding groups, the possible binding groups of your ligand, okay? You identify them. And then after that, then you look at the structure of your binding site and then compare and see like which ones are able to form, let's say, ion bonding, hydrogen bonds, which ones are able to form aromatic bonds. So you identify the different groups on your ligand and your binding site. And you, as the one operating, you are the one who has to move your ligand. You are the one moving your ligand within the binding site so that you pair them up. You pair up those binding groups. All right, and that's how it is done. And after you have paired them, you also have to, after you have paired them, then you can click on the docking procedure to start. All right, then the program will now allow the molecule to move around in that binding site, okay, as was assumed by the operator, by you, who tried to pair them up at the beginning. So after that, then the program will now try to move the molecule around within the binding site to keep pairing and making a perfect fit. Okay, and yeah, so that's with the manual one. So once the molecule has been docked, or it has been after the molecule is bound well to the binding site, there's what we call fit optimization. Fit optimization should be carried out next. Okay, so with fit optimization, this is similar to energy minimization, where you want to try and work on try to minimize the steric, the strain that is there in the compound after docking and so on and so forth. That's what happens with the manual one. So with the manual one, the concept is that you, as the one operating the computer software, you need to identify the possible binding centers of your ligand and your binding target, your target. After you identify them, then you try and pair them yourself, right? Then you command the computer to do as you have established at the beginning. That's the manual one. And there's what we call automatic docking. So with automatic docking, it's not you as the operator to decide how docking will be, but the software will decide on its own, okay? So, and how is that done? You have, the first thing also, we have issues of X-ray crystal structures being involved. So you have the crystal structure of your target protein can be downloaded on the computer. Once you download your protein, now the amino acids that are found on the binding site are then displayed. Okay, they are now displayed. You have got these different amino acids that are found on that binding site of your protein. They are displayed, while the other part of the protein is hidden. okay? And then after that, then the program, this docking automatic program would now, what it will do now, it's going to place the ligand, okay, or your molecule within that active site, okay? It will be placing them in different orientations. It will try this way, the other way, and so on and so forth. Then after it does that, then it will be able to score the different binding modes, okay? It will score it and tell you which one will give you the best fit. So it will be putting ligand in this position, it rotates it to the other position, it will keep doing that and being able to score, okay? To be scoring, and at the end of it all, it's the computer software will give you the best of them to say, this one gave the best fit, okay? Okay, and then, so the other thing is that with this software, the automatic one, there's a problem whereby, with these computers, okay, you find that it's kind of difficult for you, like certain softwares, to be able to position the ligand well in the binding site, because it's a computer, it's a software, okay? When you're doing it manually, you find that it's easier for you because you as a human, you identify to say, okay, there's oxygen here, the other, there's hydrogen atom, they can easily form hydrogen bonding and so forth and so on and so forth. That can be easily done by you as an operator. But with this, the use of different softwares, it's difficult to do that. So the issue of docking, the dock program has actually helped out in helping out to kind of identify the best fit of the ligands with the target protein, protein or target receptor or so on and so forth. So this is how the dock program would look like. You have your molecule there, and it will be able to fit it inside the binding site. Okay. So the other one, let me quickly just rush through the novo design. The novo design, what it is where you're trying to design new structures, okay? But you're designing these new structures basing on the structure of the binding site, okay? So you have a binding site, you already know the binding site within the protein to say, this drug that I'm going to form should be able to bind at that structure. So because you've got that knowledge, then you can design a drug, okay? You can design it because you know that. So in theory, you find that this can be straightforward. I mean, if I look at a protein and I see some nitrogen atoms, some oxygen, some aromatic rings, then I'll be like, oh, okay, for me to make a drug, it will be so easy. I just have to think of which aromatic ring can form van der Waals interaction, which group can I put on my drug to form ion interactions and so on. All right, so that's in theory. But again, in practice, you find that that's not the case. All right, it's not straightforward. It's actually difficult to design a drug just basing on the binding site. All right, so but with this de novo design, you find that it's good when you're trying to make a lead compound. Okay, so you look at the binding site and you assume to say, okay, I think for me to make a drug that will be able to bind or a structure here, it should have this and that. All right. So with de novo design, it's helping you to make a good lead group. But after you have made that lead compound, then you can work on it to try and do lead optimization. Okay. So what are some of the things that you need to consider as we are doing this de novo design? The first thing is that do not design a molecule which completely fits the available space in the binding site. Why shouldn't you do that? This is because, I mean, if you design a drug that is, or a compound that is able to fit completely in the binding site, it will mean that gives you no room for lead optimization. Okay, because if you do some lead optimization by adding other substituents, the structure will not be fitting well in your target site. So that is not advisable. You need to make a structure that will be loose fitting so that you can make different alterations. And then you have to leave, the second thing to take note of is that you have to leave a scope for variation in the elaboration in the molecule. What it is that this one applies to the first point. This is also helping out in the binding affinity, and when you have to talk about issues of pharmacokinetics. What if you made a compound that whose pharmacokinetics is so poor, it can't be orally absorbed, it can be easily excreted and so on. So you have to leave the variation, like you have to leave some space in this compound that you have designed where you can try and work on improving its pharmacokinetics, its binding affinity. All right. Then the other thing is it has to be the molecule that you design using the novo design has to be flexible. Okay, it has to be flexible. And then for this one, flexibility, why? Because we talked of issues of conformation. So meaning the molecule has to be flexible, because you find that it cannot be, if you make it a rigid, it will not be able to have other different conformations, you know? So it's better you make it flexible so that it can be active in different conformations. All right, so that's with that one. Now, we are only remaining with a minute. You can try and finish up now on your own, isn't it? There are just a few slides that I have, I'm sure you have read them also. These ones are talking about automatic de novo design. So please study this one also, starting from automated de novo design. Okay, somebody's so noisy. So you try and look at this one. I think we have run out of time. I can't pick it up. The automated de novo design. So it's easy for you to understand. It's just talking about how these softwares are utilized in making up a compound, like identification of the reaction site and the first step. You look at the fixed molecular fragments as the second step. Okay, the third step is where you look at the fragment bridging, where you bridge up these different sites, binding sites that you had made. Okay, so like you have identified where you identify the fragments, you now bind them, like you link them up, and then after that, you can now form a bridge and to form your molecule. So for this one, you can read on your own, the automated de novo design. All right, so if you have any question, you can ask later.